I think it should be okay for now. It's okay. Then let's get started. So today we are going to review some very basics about the generative models, especially kind of some old ideas like the GAN and the VAE before we get into the diffusion and the flow models. So I guess many of you might already have some kind of the background about the generative models. So this part might be boring for some of you, but let me just like briefly go over with some kind of the basics before, and we're gonna also see some kind of the how these kind of the ideas, the GAN and the VAE, especially the VAE, is basically connected with diffusion models that we are also going to see. So for all the generative models, the basic idea is that, as I also mentioned in the last time, the basic idea is that, let's say like we are having this kind of the very large collection of the images. So as I said, there is some kind of a data set, especially for the images, which includes the 5.8 billions of images, very large scale, the internet scales of images. So given this kind of the very large collection of the data, here the question is that how we are going to make a kind of model that can produce something that looks like one of them, right? So that's basically what we want to do. So given this kind of like very huge collection of the data points, what we want to do is that we are making some kind of the model that can produce something that looks like one of those kind of the data points. Not exactly just picking one of these kind of the given the data points, but making something new, but still that looks like one of those kind of the images. So that's basically all about the generative models, how we are going to basically make a model that can produce this kind of thing. So how can you do this? It sounds like too challenging problem. So, but the thing is that actually the course project will be really making such kind of model that can produce some kind of a new image. But that sounds like too challenging. So we are going to get into some kind of simpler case. So instead of like seeing some kind of the collection of the images, let's think about like much simpler case. Let's say like we're just having some kind of collection of the 2D points. So now we're having some kind of the lots of the dots in the 2D space that forms like this kind of shape. Okay? Then here the question is that how we can make a model that can basically pick kind of the new point, but that looks like one of those kind of given the points. So that's the basic idea, how we can make this kind of model. Actually, there can be some multiple kind of the ideas of like doing these kind of things. But what we are going to discuss in this class over the entire semester is basically seeing this problem from the statistical perspective. So we're going to say that actually everything here is basically all about the statistics. So from the statistical perspective, what we are going to see is that we are going to treat all the given the set of the 2D points as kind of the samples from some kind of the underlying the probability distribution. So we are going to assume that there is some kind of the underlying the probability distribution, which is basically defining our the data distribution. And the given set of the 2D points are basically the samples from that specific the distribution. Then the problem becomes basically how we're gonna basically sample basically new data points from that the underlying distribution. Right? So that's basically the statistical perspective of this kind of the generation problem. Makes sense? So basically, if the probability distribution is known, and for some specific types of the distribution, what we can do is that we can directly sample the data points from that specific distribution. How we can do that? Do you have any ideas for this? So we're gonna, this is basically not the main point here, but we're gonna basically very briefly see what kind of things that we can do. Let's think about some simplest case that we are having some kind of the categorical distribution. So this is even the case that we are having some kind of the discrete states, the finite number of discrete states. And for each of the states, we have some kind of the probability, which sum should be 1, right? Given this kind of the, let's say like we are having this specific the categorical distribution, having the 4 states and having some kind of probability for each of the case, right? For this kind of case, how we can basically sample one of those kind of the 4 states based on this distribution. we can do this. Any ideas? Isn't it something that you already learned from the statistics course? Yeah, I don't know. So that's basically something that we are going to do. The simplest idea for this is that we are going to see not just the probability the distribution, but the cumulative distribution, the function like this, which is basically nothing but just like accumulating the probability for the states, which is coming before each of the state. So for each of the like 4 cases, we are basically summing up the probability for the previous states. Then we're gonna make this kind of the CDF the function, right? Then what we can do is that actually we can see this kind of the CDF function not from this axis, but from the other axis here. So basically the point is that obviously like when we sum up all the probability until the last state, this sum should be 1, right? So basically, if we see the CDF function, it should be basically starting from the 0 to 1 like this. Then what we can do is that we can simply consider basically sampling from this axis. So basically, in any case, the range of the y-axis here should be basically 0 to 1, right? Then what we can do is that we are sampling from this axis with the uniform distribution, basically getting some kind of the random the probability in the range from the 0 to 1, and see where this point falls into for each of the bin here. Makes sense? That's the very basic idea for the inverse transform desampling. So we are basically seeing the CDF from the not from the this axis, but from the this axis. In terms of that, we are sampling one of the point here from the range from the 0 to 1. So that basically becomes the probability, and then see like where this basically point falls into the one of the bins here. It should be falling into the any of like those bins, right? And as we basically have some kind of the higher the probability, there will be some more the chances that the point falls into that specific bin. So it's basically very intuitive the idea, right? In terms of like how we're gonna basically sample based on the given the categorical distribution. So this is the very basic idea for the inverse transform desampling. And actually we can extend this idea not only for the discrete case, but also for the continuous case as well. It's basically exactly the same thing. So it's the matter of like given any kind of the PDF from some specific range of the some kind of data points, we are basically calculating the cumulative distribution of the function by just taking the integral onto that point, right? So given the kind of the cumulative distribution function, that what we can do is that now we are also having the same this kind of the plot, but not in the discrete space, but in the continuous space. Then we can do the same thing in terms of like sampling the probability from the 0 to 1 range with the uniform distribution and see where this point falls into the each of the infinite small bin, right? Which means that it's just like computing the inverse of the CDF function, right? So that's the basic idea. So which means that if we have the probability distribution function, if we can compute the CDF and also the inverse of the CDF, then we can use this idea to sample from that the specific the probability distribution. Make sense? Very simple. So let's do some kind of exercise. You don't need to upload this. You can just like play with this. So given this kind of the PDF, 3/8 of the x squared into this range, basically how are we gonna sample from that specific the PDF? Let's try to basically calculate this. If you have the pen and the paper, try to solve this and see what you get. So yeah, let me give you a couple of minutes to see. So over the lectures, you're gonna see this kind of the very small, tiny problems, like all the slides. So it's basically very clear to see that we can compute the inverse of the CDF like this, right? So let's do some kind of some small practices and see what you get. So yeah, here basically the point is that if we can basically have the knowledge about the PDF, the distribution, and also if we can compute the cumulative distribution the function, and also the inverse of the CDF, then based on that, we can use the simply the idea in terms of like doing the inverse transform desampling. So it's basically all about like first sampling from the any uniform distribution, and then basically fitting it to the inverse of the CDF, right? So this is the basic idea. And the thing is that what we are going to see in this class is that we are going to talk about the Gaussian distribution, the normal distribution all the time. I mean, there will be lots of things that will basically based on the Gaussian distribution. And the reason like why we are playing with the Gaussian distribution is that we know how to sample from the Gaussian distribution. That's basically very kind of the basic things. The problem with the normal distribution is that we know the form of the PDF, right? Uh, can you find the closed form of the inverse CDF of this form? If you try to find the inverse of the cumulative distribution function for the standard normal distribution, actually you're gonna see that it's not possible. So that's the problem. So we got the idea, like in the case like when we can compute the inverse CDF, then we can use the idea of the inverse transform desampling. But this is kind of the one of the representative case that we cannot directly compute the inverse CDF. So what should you do? So there are also like lots of the ideas, but I'm going to just give some kind of the basic ideas like what we can do, some very briefly. For example, so let's say for the case that we are having the standard the normal distribution, let's think about that now we are taking not only a single sample, but like taking some two independent samples, the X and the Y here, which are both coming from the same the standard the normal distribution. So in this case, the joint distribution will be defined like this, simply just multiplying these two, right? So if we just like play with the standard normal distribution like this, then there's no way that we can sample from this. So what we are going to do is that we are going to change the variables. So the idea for the changing the variable is that actually we are seeing like why we are having the two samples, not a single sample. The basic idea is that we are going to treat these like two samples as kind of the 2D, the Cartesian the coordinates. Basically like one of the points in the 2D space. In a way that we can jointly convert these two variables into the variables in the polar coordinates. So now we are going to see not the x and the y coordinates, but the radius r here and the theta here. Basically changing the variables. Especially like we are going to see not just the radius, but the squared radius, r squared there, and also the theta there. Then based on these kind of the new the variables, now we can also compute the same the joint distribution that becomes like this. And then obviously the radius and the theta, those two things will be independent of each other, right? One is about the angle and the other is basically about the distance. Then what you can see is that actually after changing the variables, we can see that we are having these two variables like this, and the probability distribution for each of them becomes like this. The good thing is that now for the angle here, it becomes the uniform distribution. So we know how we can sample from this. So it's very, very easy. The only thing is that now for the security radius, which I just denoted as the D here, that's the same as the R squared. For the security radius, we are basically having this kind of the form of the probability distribution, which is specifically the chi-security distribution with the degree of the freedom of the two, but you don't need to exactly remember this. The thing is that the PDF looks like this, right? So which means that now we know the PDF, and it looks like something that we can compute the inverse of the CDF, right? So now it becomes the matter of like how are we gonna compute the inverse of the CDF in terms of that we can sample the security radius. Can you also try to derive the inverse of the CDF? Yeah. Did everyone get this? Yeah. So I mean, yeah. So you can see like why we are changing the variables. The good thing of like that is that now we can have the form of the PDF that we can easily compute the inverse the cumulative distribution function. Then now you got the idea, right? So based on that, we can sample from the Gaussian distribution. So the basic idea is that for the angle, it's just like sampling from the uniform distribution, so it's very easy. For the security radius, what we need to do is that we first sample from the uniform sample another the uniform the distribution the sample, and then let's say computing this, right? So that becomes the one of the sample of the security radius. And based on that, it's just like matter of computing the x and the y. And the good thing is that now we get the not the single sample, but the two independent samples from the Gaussian distribution. So now you got basically the basic idea, right? So given some kind of the PDF, what we can do is that if we can directly compute the inverse the CDF, then we can basically sample based on that. By the way, all these slides are already uploaded on the Slack and also the course webpage, so you can download that. Okay. So given that the PDF, if we can compute the inverse CDF, then we can basically directly sample from that. For the other cases, we can consider doing some kind of the changing the variables in terms of that we are making the form that we can compute the inverse CDF. For the other cases, we can also do something like the rejection sampling, but we are not going to get into the deeper into that. But there are some basically a bunch of the ideas in terms like, given the PDF, how we can make some kind of the new sample. So you can see that for the cases like when the PDF is basically known, and also when the PDF is the form that we can compute the inverse the CDF, there is nothing to discuss in terms of the generative modeling. You can just directly sample from that. That's it. So nothing to discuss. That means that actually the problem that we are thinking is like much more complicated, right? So we are going to get into that. But before we get into that, here also the question is that, so that was the case of like the 1D case, right? What if we have the multivariate, the normal distribution? What should we do? The previous case was like the 1D Gaussian distribution, right? 1D standard normal distribution. For the multidimensional space, how can you do the multiple things? I mean, it's a very simple thing because like every dimension will be independent each other, right? So we just need to sample for each of the dimension because like each dimension is independent. Very simple, right? This is the case like when you sample from the standard normal distribution, when the various term there is basically the identity matrix, right? What if we have some kind of the anisotropic the normal distribution? When the variance is basically not the identity matrix. Then what we can do is that we can do something like the V parameterization trick in terms of that we are first sampling from the standard normal distribution and then computing that, which is basically just like mapping to the corresponding the point in the anisotropic the Gaussian distribution. So this sounds like for whatever the Gaussian distribution that we have, it's basically possible to basically sample from that distribution, right? So actually, that's also the reason like why we are playing with the Gaussian distribution for all the cases, because like this is the simplest form that in terms of like doing some sampling. And this was like also all the cases like when you have the set of the 2D points. But actually, what we want to do is just like not generating some 2D points. We want to make some images or videos or something 3D or something bigger, right? For the cases like when you have some lots of the images, then what we can do? So what we are going to do is that we are also simply going to treat all the RGB images, especially we are also going to consider the images in the certain resolution. Let's say like we have images in this resolution, the 256 by the 256. Also, then the question might be is that how can we also handle some cases like the varying the resolutions, right? So that's kind of the problems that we need to do some kind of engineering. But now let's think about some simplistic case that we are having the images in some kind of fixed resolution, the 256 by the 256. And then what you can see is that each of the image can be considered as kind of some sort of the very high dimensional vector, because like every pixel we have some kind of the 3D numbers, right? RGB numbers. And then we are having the 256 by the 256 by the 3D numbers that is basically representing a single image, right? So we can treat each of the RGB image as kind of like one single vector in this very high dimensional space, 256 by 256 by 3-dimensional space. Actually, every image is just like one point in a very high dimensional space, right? Then the problem becomes the same. So we are talking about the points in the 2D space. Now the set of the images can be considered in the points in this very high dimensional space. Then the problem becomes the same in terms of that if we can somehow get the access of the underlying the distributions for the set of the images in this high dimensional space, and if it looks like something like the Gaussian distribution, then we can directly sample from that. That's the basic idea. Obviously, the problem is that we don't know the underlying the data distribution. So that's the point. So how we are going to basically get the information about the underlying the distribution of the images in the high dimensional space? How we can also derive the PDF? And even in the case that we know some kind of the have some information about the underlying the distribution, can we sample from that? Which means that we also should be able to compute the inverse of the CTF, or we need to do something, right? So that's kind of the problem. So basically, the only information that we have is just the samples that we assume that these are samples from some kind of certain the underlying distribution, but we don't have the information about the underlying distribution. So in this case, that we don't know some kind of information about the underlying distribution, how we are going to sample from it. So that's the problem for the generative modeling. So the very basic idea for not only for the diffusion and the flow models, but for all the generative models is basically is this. So what we are going to do is that we are going to find a mapping from some kind of a simple distribution that we know how we can sample from it to the data distribution that we don't know. So we don't have the information about the data distribution, but we are going to consider finding a mapping from some simple distribution, which is typically the standard, the normal distribution, because we know how to sample from this, right? And then we are mapping the whole distribution into the unknown, the data distribution. So that's basically what we are going to do. So what we are doing with the either GAN or the VAE diffusion or the flow model is basically all about finding this mapping from some simple distribution to the data distribution. So over the entire semester in this class, we are going to use these notations. Here, basically, Z represents some kind of the samples from some that simple distribution that we are also going to call as the latent distribution. So Z basically means the sample from the typically the standard the Gaussian distribution, and the X denotes the data point. This is one of the real data point that we have in our training data set, right? And PZ, the latent distribution, is the information that we know, and the PX is something that we don't know, right? So that's basically the setup of the entire this semester. So the generation process will become basically we are sampling from the latent distribution, the standard, the normal distribution, and the mapping this into one of the data point. That will be our generation process for everything, for the GAN, VAE, diffusion flow models, for everything. Make sense? And here then the question is that how we can find such kind of the mapping? How do we know for such kind of mapping? So that's the kind of the place where the neural network basically comes in. We are going to train a neural network in a way to basically find the mapping from one of the samples from the latent distribution to one of the samples from the data distribution. So that will be the role of the neural network for all these models. Then in terms of like finding this mapping, we are going to see. So this is basically kind of similar with the autoencoder. I guess everyone would know about the autoencoder. Is there anyone who didn't hear about the autoencoder before? Yeah. Yeah. So very basic things about the deep learning, right? So the goal of the autoencoding is basically to some kind of do some sort of the compression, right? So here we want to map any kind of the input data point into the latent data point. And the idea of like this mapping is that we are having the encoder and the decoder in a way that the decoded output should be the same with the input there, right? So that's the basic idea. And what we can say is that here the encoder becomes the function which is mapping the input data point into the latent data point, and the decoder becomes the mapping from the latent data point into the input data point, right? So in our context, this is the X, the data point X, and this becomes the Z, the latent sample, which is typically coming from the Gaussian distribution. And then you can see that the encoder is mapping from the X to Z, and the decoder is the mapping from the Z to the X. And what we need is actually just the decoder. We don't need the encoder, right? If we can basically have some kind of mapping from the latent to the data point here, then we can use that in our generation process. So the problem is that then how we are going to train this decoder while guaranteeing that basically all the samples from the latent distribution basically go to one of the data points in the data distribution. So for that, we are seeing some kind of the bunch of the ideas like the GAN and the VAE for many things. For many of you who already know about the GAN, so let me, this part might be boring, so let me go quickly with the GAN. So the basic idea for the GAN is that actually it's coming from the idea of the adversarial attack. So the basic idea for the adversarial attack is that we know actually neural networks are quite good at for many things, especially for the classification. Neural networks are really good at classifying the truck and the whatever, some buildings or something, some other kind of some dogs or something, right? Here the thing is that these are all the images that are collectively declassified with the pre-trained model. And what if we add some kind of the small noise into these images? The thing is that I don't know whether you can see any kind of difference. Even for me, actually, I cannot tell any kind of difference between this and this. But actually, the middle column here are basically visualizing the difference between these two images. Also multiplied by 10 in terms of like amplifying the difference. But basically, these two are almost the same images, while basically adding some small, tiny noise over the images and making some kind of slightly different images. The thing is that if we add this kind of noise into the images, the thing is the pre-trained the classifier will see all those images as the ostrich. Do you guys know the ostrich? This one. Somehow, like the pre-trained classifier are basically seeing that these images are in the same class with this bird, right? So that's kind of the idea of the adversarial attack. Well, basically checking how vulnerable the neural network is in terms of basically, even when you add some small noise into the input data point, how much it will be basically declassified the old images in the correct way. So that's the basic idea. So this is basically the task which is called the adversarial attack. We are basically making a neural net in a way that the output of the neural net becomes something that makes the pre-trained the classifier to fail. So that's the basic idea for the adversarial attack. Then when we have this kind of the neural network that plays the role of the offense, then we can also fine-tune the neural network for the defense, right? So we can consider also basically fine-tuning the neural network in a way that the network also does not fail for those kind of some degenerated images, right? So that's the basic idea. Then what we can do is that we can make them to compete each other. So when you make some kind of some healthy competition between these two neural networks, we can basically consider making those the two networks to improve each other in terms of like this is like making some kind of the better images, and also this one is also doing some kind of better classification. So that's the basic idea for the GAN. I guess most of you already know. So we are basically making a discriminator, the classifier, which is classifying whether the output is some kind of the real image or fake image that we are generating using the generator. And also we are having another generator, which is making some kind of some real-like images. So in a way that we want to basically fool the discriminator, right? So that's the basic idea. So in the context of the generative models, we can see that the generator is basically the decoder in the autoencoding setup, which is basically taking the sample from the latent distribution and then mapping it to one of the realistic data point. And then the discriminator will play the role of basically classifying whether the output is something that is the real image or some kind of the fake image, right? And then we are making them to compete each other. So if we briefly go over into the loss function here, so this is the loss function which is training both the discriminator and also the generator. The meaning of this loss function is that basically we are taking the sample of the real image, the data point coming from the training the data set, and also the point coming from the latent the distribution, right? Typically the standard Gaussian distribution, and then mapping this like latent sample into our generator in terms of like making some fake image here, right? And then what we get with the discriminator D here is basically how likely the input image will be the real like the image. So we are getting some kind of probability of like how likely this input will be one of the real images. And we can see that this is kind of the optimization the problem that we are maximizing the loss function over the parameters of the discriminator, which means that so maximizing all the loss function basically means that we want to increase the probability of this. Obviously, this is the real image sample, right? So we need to maximize the probability of like how likely this would be the real image, right? So we should be maximizing this. And then this is the 1 minus like the term here, right? So which means that we are going to decrease this. So we obviously the probability of like how likely this like fake image will be treated as kind of the real image should be decreased, right? So this is the design of the loss function in terms of like increasing that and then decreasing that by basically maximizing the parameters over the D. And then from the perspective of the generator, actually we are now increasing the probability. So now in this case, like we are optimizing over the parameters of the generator here in terms of that we also want to make this like fake image to be treated as some kind of one of the real images. So we can see some kind of the competition between this like the discriminator and the generator in this term, right? In this loss function. So we can see that this is kind of the optimization the problem, which is basically having the combining both the minimization and also the maximization. So for the some parameters of the neural network, we are maximizing this whole the loss function. And for the some other the part of the neural network, we are minimizing this loss function. So this is basically very well-known some kind of the optimization the problem in terms of that it's really hard to solve. It's very easy to basically get into some kind of the local minimum. So that's actually the problem with the GAN. So when you train the two neural networks with this kind of the minimax the optimization the problem, there are lots of the chances that we get fall into some kind of the bad the local minimum. So that's the problem. So the typical the failure cases of the GAN is that is there anyone who tried to implement and train the GAN before? Have you experienced any kind of problem from the GAN training? Yeah. Anyone?
Impossible to one training it keeps shifting. Like,
yeah. So it's also there are lots of the issues. Like it's basically hard to see some kind of the convergence of the loss. And typically the problem is that many failure cases that you can easily see with the GAN training is that the discriminator typically wins. It's very hard, very easy to see that the discriminator basically converges faster. And then this basically results in that there is nothing learned with the generator. So it's kind of also the life lesson, right? I mean, for all the things that we are doing, if you first set some kind of very strong criteria for the success, then there is nothing we can do. I mean, the criteria is already too strict. So there's nothing we can want to try, explore, right? So that's also the very typical the failure cases of the GAN training. So the typical some practice for the GAN training is that you first need to train the generator first without training the discriminator in terms of that the generator can produce something. And after that, you also need to basically combine both the generator and the discriminator in terms of like making them to compete each other. But for many of the cases, you can see these failure cases that the discriminator basically becomes too strong in terms of the generator learns nothing. So that's the typical failure cases. And also the other problem of the GAN is that even in the case that when the training goes well, there are also lots of the cases, it only learns some kind of the subset of the distribution of the data points. So especially for the cases that when we have some kind of the multiple the modes like this, multiple some kind of some small groups of the data points in the space, the output basically learns that not the entirely distribution, but only capturing some kind of the subset of the modes in terms of like losing some kind of the diversity of the data points that we have. So this is like very typical the failure cases. And if you try to train the GAN yourself, then you're gonna see that actually the training GAN is really, really, really difficult. So you will need to do lots of the engineering. So these days, like for many kind of the companies, I think there is no really any kind of like Gen AI teams really working on the GAN things. But until like 2020, I think all the like Gen AI related kind of the teams in the companies were really implementing GANs for the image generation or the video generation for the many things. And they even have some kind of some dedicated engineers. The engineers are just like tuning some parameters of all the things in terms of getting some kind of better performance. Even not just like one, multiple people are just like tuning all the parameters in the GAN training to better capture all the diversity. While it's really, really difficult. So that's like very hard jobs. But still, this is the very basic idea. After the first idea of the GAN has been introduced in the 2013, there have been lots of different variants of the GAN, as you can see. This is even not the full list. So there are also some of those are very successful, the examples, like really making some kind of realistic images. So as I also showed in the last lecture, these results of like making the face images was based on the style GAN tool, which was introduced in the 2019. So even at that time, without any kind of diffusion flow models, you can see that actually the quality was not bad, right? Making something quite realistic. So the reason, I think the main reason like why people shifted to the diffusion and the flow models from the GAN is not just because of the quality, but actually because of the difficulty in the training. So even with the GAN, if you do lots of the engineering or the many things, then you can manage to get some kind of quite good quality of the outputs. The problems are the two problems are basically the difficulties in the training and also the diversity. So there are quite many cases that like basically losing some kind of the diversities for the outputs. So that's kind of the issues with the GAN. So that's why also people started to consider some kind of new idea, which is the VAE, the variation of the autoencoder. So here the question is that how we can basically train the models without solving the minimaxity problem. So for that, basically what we are going to do is that now we are going to see the mapping from the latent distribution to the data distribution, not just like finding the function, but actually learning some kind of the conditional distribution. So here, basically what we are going to see is that we are going to see this kind of like mapping problem as kind of another desampling the problem. Given any sample Z there coming from the standard Gaussian distribution, how we are going to basically learn this like the conditional distribution in a way that we can sample the X, the data point, conditioned by the Z, which is coming from the standard Gaussian distribution. So that's the basic idea. And we are going to simplify all the things. It doesn't need to be Gaussian distribution here. We are basically for many things, we are going to use the Gaussian distribution because of the simplicity. And then we are going to model the conditional distribution in this specific way. So basically the variance is kind of like fixed. So we are basically fixing some kind of the variance. We only learn the mean here. And this like mean is basically learned by the decoding neural network. So that's the basic idea. So somehow if we can basically learn this kind of the conditional distribution, based on that, what we just need to do is that we just sample the Z here. And based on the sample of the Z, we also sample the X. And that's it. So that becomes of our generative models. Then the question is that how we are also going to learn this kind of the conditional distribution, right? So that's the problem. So you see that all the VAE and also diffusion models are all about basically learning this conditional distribution. So that's the point. So before we get into some details about that, I'd like to very briefly review some very basics about the statistics. I guess all of you would know about like those things, but let me check whether you really know some details here. So basically, what's the marginal distribution? So marginal distribution is the distribution for the subset of the variables. So when you have some kind of the multiple the random variables here, given this kind of like joint distribution, the process that we are getting some kind of the distribution for the subset of the variables is called the marginalization. So this is the case that like when you have the two variables like the X and the Z here, if we take the integral of the Z here, then this becomes the marginalization for the X. Basically getting some kind of the probability distribution, not for those two, but only for the X here, right? So that's the process that we're gonna call as the marginalization. Then here the quiz is that, so let's think about this. So given this kind of the joint probability distribution, we are having the X and the Y, and each of the X and the Y can have these one of those three numbers, like either 1, 2, or 3, right? Given this kind of joint probability distribution, what's the probability that the x becomes 1? You can just speak up. 0.36. Do you see like why 0.36? So it's taking the integral, right? So which means they're just taking the sum, right? So if we want to get the probability for the x becomes the 1, then we just need to take the sum for this, right? That is like taking the sum along this axis, like this things becomes the marginalization with respect to the x, right? We are getting this some kind of probability distribution with respect to the only the x. So that's the marginalization. Everyone knows the expected value, right? So basically, it's the weighted sum of the some possibility values that we can take weighted by the probability, right? Here, right? So we can also compute the expected value for the x here. So what should we do if we want to take the expected value over the x here? Very easy thing, right? I mean, we just need first to marginalize the joint distribution along like just taking the sum here. And then just like taking the weighted average with these three numbers with the marginalized probability, right? Then you can also compute the expected value as well. Right? These are all the things. The base rule, this is the basic things like the joint distribution here can be basically represented with the products of the conditional distribution and also the some marginal distribution here, right? So here basically some kind of the terminology that we are going to use that. So as I said, we are going to keep using basically these two notations. Like z is basically the variables of the latent distribution, and the x is basically the sample from the data distribution. We know which one we know. The information that we know is basically the latent distribution, right? So this is basically the prior knowledge. So we are going to call this prior distribution, right? So given the prior distribution, the conditional distribution, the probability of like the x, given the one of the sample of the prior distribution, will be called the likelihood distribution. So this like likelihood distribution is about like how likely we are going to sample this x, given the latent variable z here. That's the likelihood distribution. I mean, it's just like terminology. So because like you're gonna say that like this is like x conditioned by z and z conditioned by x. Like what's the meaning of like having the two different names for these two, right? So the reason like why we're having the different name is that basically this is the prior distribution that we know, and this distribution is the marginal distribution with respect to the x, which is the unknown information, right? So what we are going to do is that given the prior distribution, actually this is something that we want to get, right? Given the z, we want to get the likelihood distribution in terms of that we can sample the x given the z. And sampling x basically means like generating the x, right? So this is about our generation process. So basically by multiplying the prior distribution and the likelihood distribution, we can get the joint distribution here. And the posterior is basically the opposite. So given the data point, what would be kind of how likely it would be sampled from the parameter z here. So that's the opposite of the likelihood distribution. So this is the distribution we're going to call the posterior distribution. Okay. So don't get confused. Like you're going to say like we're going to see lots of like those things like x conditioned by z and z conditioned by x. Like the meaning of like all the thing is that we are starting from the prior distribution and then we are going to sample the x from that. So this is something that we want to get, the likelihood distribution. In the process that we are basically learning the likelihood distribution, we also need to see lots of things about the posterior distribution as well. So that's kind of the terminology. So here's the one quick question is that then how can we compute this conditional probability? What's the probability of the y to be 2 conditioned by that x becomes the 1?
1 over 12.
1 over 1 over 12. Yeah, why is that? Can you see like how can you compute this? Very simple thing, right? So from the base rule, basically what we can see is that this probability multiplied by the p, multiplied by the probability of the x equals 1 should be the joint probability, right? So from the marginalization, we can compute the probability of the x becomes the 1. And we also all have the information about the joint probability, right? So based on that, we can now compute this as well. So these all can be computed with the base rules. And the pullback, the liberal, the divergence. So this is all about the measuring some kind of how much the given the probability distribution, the p is basically different from the some kind of reference distribution, the q here. So it's basically some kind of some notion of the distance between the two probability distributions, but actually it's not distance because it's not symmetric. So when you basically change the p and the q, when you switch these two, the quantity of the pullback, the divergence will be changed. So you can think it's kind of like some asymmetric way to measure some kind of not exactly the distance, but some kind of how much some kind of the given distribution is like far from some kind of the reference distribution, the Q here. So this is kind of the way to measure some kind of some difference between the two distributions. And then here the question is that what would be the KR divergence for the case when the given distribution is the same with the reference distribution? Should be 0, right? I mean, by definition of our KR divergence, this should be 0. And you can also really check out that whether this formulation goes to 0 when these two distributions are the same, right? So this is the basic idea. And I think we don't have time to work on this for now, but I'd like to ask you to basically check out how we can exactly compute the KR divergence for these two Gaussian distribution. So as I said, all of our things that we're gonna play with in this class will be all based on the Gaussian distribution, which means that we should be able to also measure the KR divergence for these two distributions as well. So check out how we can exactly compute the KR divergence between the two Gaussian distributions. And one more thing is that, so let's briefly talk about the convex function. So the meaning of the convex function in the one-dimensional case is that basically the function that looks like this, having some kind of the curvature into the downward. So the precise way to define the convex function is that when you take any kind of the 2 points here, if you take the linear interpolation between the function values of these 2 points, then all the linear interpolation will basically form this kind of straight line, right? So when you see here, the linear interpolations of the function values, if you take the interpolation between the function values of these two, that will basically form this line, right? For whatever t in the range from the 0 to 1. And if we see that, not taking the interpolation for the function values, but if you take any kind of the intermediate data point here and take the function value of that point, if this value is basically lower than any of the values in the straight line, that's the case that we are having the convex function. For any kind of the 2 points, for any arbitrary 2 points, if we draw basically the straight line, and if we see that all the intermediate the points, for all the intermediate the points, if the function value is basically same or the smaller than basically the function value of this straight line, that's the case that we are having the convex function. Right? Then what would be the concave function? Obviously, the concave function will be the case that we are flipping this sign, right? Then that will be the case that we are having the function that looks like this, having the curve to the upward, right? So this is the case that we are defining the convex function in the 1D case. Obviously, we can define the convex function not only in the case, but for the arbitrary dimensional space. So in any kind of the high dimensional space, if we have a function that satisfies this for any data points, the x here, for any number of the points, when you take some kind of applying the combination of the function values. So for some of the cases, like for the 3D case, for example, like you can consider like, it's the case that we are having some like 3 points, making some kind of plane in the 3D space. And for all the intermediate, some kind of the points in the domain space, if we take the function value, if the value is basically lower than the plane, then that's the case that we are making some kind of the convex function, right? So we can also extend the concept of the convex function, not only for the function in the one-dimensional space, but for the any high-dimensional space. Obviously, the sum of this t here should be the 1 to make some kind of the affine decombination. Make sense? Clear? So this is the case like when you have some convex function. So I mean, this is the definition of the convex function. And based on that, what we can see is that the Jensen's inequality is basically nothing but when these ti, the weights, the ti is not some kind of the arbitrary values, but some kind of the probability. So now let's say that for each of the xi here, we have not only the function f, but the probability distribution defined on the same domain space. For the case, if we also replace all the arbitrary t here into the probability for each of that point, if the function f is the convex function, then the same thing should hold, right? So what we can see here is that this is exactly the same formulation in the formulation in the previous slide. The same thing. The only thing is that now we are having probability for each of the data point here, given any kind of the PDF. So it's just like simply replacing this t as kind of the probability for any kind of the probability distribution defined over the space. In that case, the definition of the convex function should go in the same way, right? And now when you have the probability here, now we can rewrite these parts into the expected value. So that becomes like this. So if x is a random variable and also the f is a convex function, then any kind of the probability the distribution, this basically the definition should hold, which is basically exactly just coming from our definition of the convex function. Make sense? Nothing special. It's basically very simple kind of things. And also for the concave function, that will be the case that we are flipping this sign into the other way around. It's clear? Any questions on this? So this is like basically the basic idea about like all the kind of things. So going back to the VAE, basically what we wanted to do was that we wanted to basically learn this like likelihood distribution in a way that we can sample from the Gaussian distribution and also sampling the x be conditioned by the z. So that's basically what we want to do. Then, as I said, like what's the question here is that, so, and also we are having this specific form of the likelihood distribution in this way, right? It does not need to be Gaussian, but we are just simplifying everything into the Gaussian in this case. And then here the question is that how we can learn that the likelihood distribution. So that's the question. So what we can do is that we know this, right? We know this, and we have lots of the samples of the x. This is our training data, right? Then what we can see is that from the marginalization, if we have like know this and also the likelihood distribution this, from the marginalization, we can compute the probability for the given data point. And obviously, if we have some kind of the likelihood distribution, this probability should be high, right? Because these are some of the samples that we know coming from the data distribution. So which means that we can consider like finding some likelihood distribution in a way that that basically maximizes the probabilities for all the data points x here. That's the basic idea. Make sense? We know this probability. We're also sampling the z from the Gaussian distribution. And then if we can compute this, based on that, we can compute the likelihood of the x. And then we want to basically maximize this probability by finding some good likelihood distribution this. The problem of like all the things here is that this basically involves the integral integral over the z, which means that we need to compute this not only for some single z, but basically need to take the integral over the entire space of the z. How we can compute the integral in this case? So actually, that's the issue. Some kind of the simple way of like doing this is that we are doing some kind of some approximation. That's the process called the Monte Carlo method. Nothing but just in terms of like taking the integral, the way to simply like approximating this is that we just take lots of the samples of the z, yeah, and just taking the sum of this. That can be like one way to somehow approximate this integral right here. But if we want to get some kind of the really accurate approximation, then we need to really have tons of the z here. This will involve huge computation, which because like just to compute the probability for the single data point dx, we need to actually have some lots of the samples from the Gaussian distribution. That makes some kind of lots of the burdens in the computation. So that's the problem. We want to basically find the likelihood and maximize the px here, but we don't want to really compute the integral. So that's the kind of the main things. So how we can do this? It's kind of the interesting the idea. So that's basically why the posterior distribution comes in here. While we want to basically learn the likelihood distribution here, actually now we want to compute the marginal distribution, the px here, by leveraging some kind of the information about the posterior distribution here. So if we know both the likelihood distribution and also the posterior distribution, based on that, without really taking the integral, we can compute this, right? From the base rule that we have seen in the previous slide. This is clear? Then what this means is that now we need to have both information, both the likelihood distribution and also the posterior distribution. Then based on that, we can basically consider jointly learning these two in terms of like that we are maximizing the px. Obviously, the problem is that we don't know not only the likelihood distribution, but also posterior distribution. We don't have this information. So that's also another problem. So what we are going to do is that, so this is basically the key idea for the VAE. And also we are going to keep seeing this like same kind of the formulation also for the diffusion models for the other things as well. So since we don't know the posterior distribution here, the z conditioned by the x, what we are going to see is that we are going to instead see some kind of the lower bound for the marginal distribution. But what the basic idea is that what we want to maximize is basically this, right? We want to maximize the probability for the data point here. But since we cannot directly compute this, we are going to consider the lower bound of this probability, which is defined like this. And here the thing is that this looks very similar with the previous form here, based on the base rule. But the kind of the difference is that now we are having not the exact the posterior distribution, but some sort of the proxy distribution. Something that is not exactly our the posterior distribution, but some random the conditional distribution, the distribution of the z conditioned by the x. So by having some kind of some proxy distribution, we can consider basically define some kind of the lower bound of the marginal the probability, and then basically we can learn this kind of the likelihood distribution. So this is the main idea, but I think we discussed too many things today. So next Monday, we're gonna continue discussing this like ELBO, the loss function, and see based on this how we can train the VAE, and then we're gonna continue how this idea also can be extended to learn the diffusion models as well. So this is the end of this class.